So this lab's pretty straightforward. In fact, in Science 10, you may have done a similar procedure, okay, to this one. We'll be doing a slightly different analysis than you would have done in Science 10, but essentially the procedure would have been the same. We're going to run this thing down a ramp, and we're going to measure how far it travels after the bottom of the ramp, and we'll be able to determine from that, okay, how much kinetic energy it had at the bottom of the ramp. Okay, we'll be able to calculate how much potential energy it had because we can measure the height of the ramp, okay, and we'll compare those two values, right? That's what we're looking at here, is comparing the potential energy at the top of the ramp to the kinetic energy at the bottom of the ramp, right? That's the whole purpose of this lab, okay? So our variables, okay, if we're looking at how we're setting this up, okay, we're going to run 4 trials, but they're all going to be with the same ramp. We're not going to alter the ramp at all. We're just going to make it so that it's got some height, and we're just going to run 4 trials so that we can get 4 sets of data and average them, just to kind of help eliminate any error if we get one wonky one or something like that. Okay, so we're going to run those trials. Okay, if we're trying to compare potential energy at the top, or mechanical energy at the top, to mechanical energy, kinetic energy at the bottom, right, then we don't get kinetic energy unless we start with potential. Okay. So we don't even have a lab if we don't have potential energy at the beginning, right? We are doing work, we're giving it potential energy, okay, at the beginning of this lab, and that amount of potential energy is what's going to determine how much kinetic energy it has at the bottom. Okay. Now, we can't directly measure the kinetic energy at the bottom because we can't measure directly how fast the object is going at the bottom of the ramp. So what we're going to do instead is measure how long and how far the cart rolls for after it leaves the ramp. Okay, what's going to stop it at that point? Friction. Okay, friction is going to bring that cart to a stop. I'll be able to determine how much work is done against friction by taking the distance it travels, the time that it travels for, okay, and I'll be able to calculate the acceleration, okay, and then I can go mass times acceleration times distance, in other words, force times distance, okay, and I would have then, okay, the amount of energy it lost after it got to the bottom of the ramp. That has to equal the energy it had at the bottom of the ramp. Right, so because we can't actually determine V at the bottom, we have to indirectly determine it another way. Right, so we're measuring quite a few things, but we're only comparing 2 things. We're comparing potential energy at the top to kinetic energy at the bottom. Okay. All right, you guys can think up controlled variables. Okay, like I said, it's going to be that apparatus. We're going to run it 4 times. Okay. Some things that would be the same, right? Something that people have been missing as a controlled variable in the last 2 labs, odd, but people haven't been listing it. But it affects this lab, it affected the friction lab, and it affected the Newton lab. What is it? Gravity. Okay, but I haven't had a lot of people list that as a controlled variable because I think their mindset is, I'm not controlling gravity. Well, yes, you are. Because you're doing the lab right here, and gravity isn't going to change during the course of the lab, not significantly enough to alter anything we're doing. All right. So I would mention that as a controlled variable. You're welcome. All right. For our hypothesis, okay, we need to have a hypothesis that talks about the mechanical energy conversion that's going on here and the law of conservation of energy. So I would suggest the if part should talk about the law of conservation of energy and what it says. Okay. You can do this from 2 perspectives. You can look at the law of conservation of energy from an ideal perspective, okay, like it's in the perfect physical world, this is what it says, or you can look at it from a real world perspective. It still says energy can't be created or destroyed, but in the real world perspective, you might mention other forms of energy, okay, that might come up. The and part, as always, is going to describe the experiments. And the then part, you need to tell me what you think will be the relationship between the kinetic energy at the bottom and the potential energy at the top. That's EP initial and EK final. Okay, a couple of things you'll need to keep in mind for calculating things in your analysis. Okay, there's some variables that we're going to need to know. First variable is that we need to know the mass of the cart. Okay, the mass of all of these carts is 475 grams. However, I would suggest it should be used in your calculator like that. Okay. Other things we need to know. Okay, the height of the ramp. So you're going to need to use one of the meter sticks to measure how high the top of the ramp is, okay, when you get the ramp all set up. Okay, so you'll need, mass of the cart, initial height of the ramp, and obviously 9.81, okay, to calculate potential energy. To calculate the kinetic energy, we're going to need the mass of the cart, which we have, the distance traveled by the cart after it leaves the ramp, and the final velocity, which will be 0, and the time it travels for. Right? Those are the things we're going to use. Okay, things we'll have to calculate. We'll have to calculate the acceleration of the cart, and we're going to use this formula here: A equals 2 times d over t squared, which is essentially just a manipulation of VF times t minus 1/2 at squared, just manipulated for A. All right, so it'll be 2 times d over t squared. That'll give us our acceleration. That's why we need to know the distance. Okay, we know final velocity is 0 and time. That way we can get acceleration. Right? We're going to solve for kinetic energy by using the force of friction. Okay, we're going to say that friction is what steals all the kinetic energy from the cart at the bottom of the ramp. Right? So we have to wait for friction to do its work and stop the cart. Then we can use the distance it traveled, okay, the acceleration of the cart, and the mass of the cart, okay, to find the work done against friction. In other words, the kinetic energy will be equal to the work done against friction, mass times acceleration times distance. I can use m times a because at the bottom of the ramp, friction will be the only force stopping the cart. In other words, it's also the net force. That's why I can use m times a. Right? So if I go m times a times d, that's force times distance. We're changing the kinetic energy. It's net force that changes kinetic energy. All right. Okay, and then potential energy, obviously we'll just use the potential energy formula, m times g times h, okay, and we'll have all the numbers we need to do that. So the procedure will work as follows. You'll set up your ramp. You don't need to make it very tall. In fact, if you make it too tall, the cart will go too far, and it'll just take forever to measure, okay, or it'll hit walls or other things, okay? So we don't need the ramp to be very high, okay? I've got 3 like thin textbooks, right, stacked underneath that ramp. So they're these red ones here. Okay, so it's not very high. Okay, these are maybe 4 centimeters thick each, right? So I've got maybe a 10 centimeter, 12 centimeter high ramp. That's all you're going to need. A couple of binders would be lots. Okay, we just need to give it enough potential energy that it can roll off the end of the ramp. Okay, so you're going to have that set up. You'll put the cart at the top of the ramp, and then you're going to hand time this. Right, we're not going to use the sensors because they're more trouble than they're worth for this lab. Okay, so we're just going to run the cart down the ramp. When do you need to start the timer? When the cart hits the floor. Okay, we're only worried about the deceleration part. Okay, when it's slowing down due to friction. So we only want to time that part. You'll have, because you're not making a steep ramp, reaction time is not going to be a big factor, right? Because you'll be able to watch the cart go down and then anticipate and go, right? And of course, because it's rolling to a stop, you'll also have lots of time to be ready to stop the stopwatch as the cart slowly rolls to a stop, right? So reaction time is not going to be a huge factor here, so we can hand time this. So we'll need to time each trial, and then we'll need to measure how far the cart goes on each trial. In order to do this most effectively, because you're doing 4 trials, take a board marker. Okay, when the cart stops, mark where it stops. Thank you. Okay, mark where it stops on the floor and just put a number. So, like I would say, mark on the floor so it looks like this. Okay, that's trial 1. That's trial 2. Okay, whatever. Just mark on the floor there. Then measure them all at once. Okay, way easier to measure them all at once because then you won't have to measure. If it travels 4 meters, okay, you can go, okay, 1, 2, 3, 4. Well, they all go 4. This one went 4.05. This one went 4.2. This one went, okay, and you won't have to measure the whole entire track again. Okay, so you'll measure distance, you'll measure time, and then that's it. Okay, that's all you have to measure. Then you're moving into the analysis, and you are filling in the data chart, which I don't have there. Okay, but you'll fill in the data chart by calculating potential energy. You only have to calculate that once, right? Because it's the same each time we're doing it. You will have to calculate the kinetic energies each time because it'll probably, the distance of travel will be slightly different each time, and then answer the rest of the analysis questions down below here, right? So calculate the work done in putting the cart on the top of the ramp. Okay, again, you're giving it potential energy, so you should be able to calculate that one pretty easily. Okay, calculate the acceleration of the cart using this formula for each trial. Calculate the kinetic energy, m times a times d. And then 4, 5, 6, and 7 are the questions that are your true analysis. Okay, these are calculating the numbers you need, and then 4, 5, 6, and 7 are, okay, analyze what your data says to you. Okay, so just make sure you give good, thorough answers for 4, 5, 6, and 7. Your conclusion, same as always, restate your hypothesis, and then explain if your data accepts or rejects it. You'll probably, this time, possibly depending on how you write your hypothesis, have to reject it. If that's the case, make sure you say why. Okay? Talk about where some of those forms of energy or where that energy may have gone, what forms of energy might it have turned into, okay? Things like that. So it might not be a bad idea to have one person timing and another person taking a video. Okay, take a video of the thing so you can watch it again, and that might help you to determine where some of the energy goes during the runs. Okay, yeah, and then evaluation, sources of error, ways to improve them. Okay, same as always. Questions on what we're doing? Okay, I also have the biology lab booked for this, so we can spread out a little bit. Okay, that way we can probably have like 3 or 4 groups in this classroom. We'll just widen a couple of rows, and we'll put 3 or 4 groups in the biology lab. Just make sure you got a nice long clear path that you can use, okay, for this lab. Okay, all right, let's get to it.